I think we can start, and it's my great pleasure to introduce Professor Eitan from the University of Maryland to be here to give a welcome talk. Professor Tadmor is a distinguished university professor at the University of Maryland, College Park, and the director of the University Center for Scientific Computation and Mathematical Modeling. Professor Tadmor's primary research interests include analysis of time-dependent problems, development of high-resolution algorithms for the approximate solution of such problems, and the interplay between analytical theories and computational aspects with applications of shock waves, kinetic transport, incompressible flow, image processing, models for organized dynamics, so we will see today. Professor Tadmor received his PhD in mathematics from Tel Aviv University in 1979, and he began his scientific career as a Bateman research instructor in Caltech. He held professorship position at Tel Aviv University, where he chaired the Department of Applied Mathematics, where I was a PhD student at the time Professor Tadmor was chair. And at UCLA, where he was the founding co-director of the NSF Institute for Pure and Applied Mathematics. Since 2002, Professor Tadmor has served on the faculty of the Department of Mathematics and Institute of Physical Sciences and Technology at UMD. And in 2012, he was awarded as a PI of NSF Research Network and a description of emerging challenges in natural sciences, which is called Kinetic. Professor Tadmor has held visiting positions in many universities, including University of Michigan, Paris 6, Brown, Ford Institute, Weizmann Institute. He serves on the editorial board on more than a dozen leading international journals and has given numerous invited lectures, including plenary addresses at the International Conference of Hyperbolic Problems and an invited lecture in 2002 International Congress of Mathematicians. In 2015, Eitan Tadmor was awarded the Siam ETH Peter Henrici Prize for regional, broad, and fundamental contribution to the applied and numerical analysis. Professor Tadmor is an AMS fellow who was listed on the ISE most cited researchers in mathematics. He has published more than 150 research papers, mostly in numerical analysis and applied partial differential equations. Please.
Thank you for coming for my lecture. I want to thank in particular two people, Gilles Lee, who was instrumental in inviting me here. And despite this long introduction, I would like to express my appreciation to your chair, whom, as you understood, I know for many, many years. You have a really great chair, and I'm a great fan of her. So thank you, and despite this long introduction. And without further ado, let me tell you a story about this collective dynamics. It's rather broad in perspective, and I will share with you my experience in the last 5 or 6 years, which is one of my main research avenue. This is specifically, I will tell you a little bit about joint work with my counsel and senior here, former postdoc Sebastian Roach, and former student Jean Eitan. So let me start, first of all, the general structure. I will assume that some of you are familiar with this topic, but some of you who are not. I will start with the basic paradigm of environmental averaging. I will provide 3 or 4 canonical examples for collective dynamics. I will focus on the mathematical aspects of collective dynamics, and then I will address 2 questions which are of importance: the large time behavior and the behavior for large curves. So this is the plan. And let me start at the beginning with something which is reasonably simple, and this is this basic paradigm of environmental averaging. And here is what I will talk for the next hour. We have a collection of agents. This capital N typically is much larger than 1. Each one of these agents is identified by a vector of properties or traits, which I will denote by P, or properties. And here's the simple dynamics is environmental averaging. Every agent, let's say me, take a convex combination of the average of my neighbors, which are identified by the vector of properties of each. This is it. That's what I'm going to spend the next hour. And the weights, notice that they add up to 1, and I assume that they are non-negative. We can write it slightly different. taking into account that the sum of the Aij is 1, if we subtract pi from both sides, and then we divide by delta t, now we get the same statement but viewed from a different perspective, where the rate of change of my property is proportional, alpha is the frequency, to a weighted average for the difference between my property and the property of my neighbors. So what you see here is a discrete gradient when we take into account all the j's. And this is a statement that I'm changing my property by trying to align my property with the properties of my neighbors. Hence, we call this process as an alignment process. We are just trying to adjust to the neighbors try to adjust to their neighbors, and so on and so forth. So this is the seemingly simple framework, which I'm going to spend an hour. So where is the delicate point? The delicacy comes with the weights, which we will assume to be non-linear. And here's an example. We take the Aij to be a function, or we call it the influence function, depending on my state and the state of my neighbors. It's assumed to be non-negative, and it's normalized by something called a degree, so that the Aij sum up to be 1. The influence function, later on we will give example for that, are problem dependent and depends on the specific model and the specific context, which comes from very different background. So here's the degree, and it's the total amount of influence on agent i's, and I should mention that this is really the notion of degree in graph theory. So it is consistent, and even though there are many observations from completely different models in different contexts, nevertheless, despite this variety, there are some similar fundamental features in these collective dynamics which are governed by this type of models. And in particular, when there is a large number of agents, there's the emergence of large-scale coherent structure like swarms, colonies, parties, cluster, consensus, and so on. They come from different contexts. I would like to talk about this in context. Before I do this, before I get really to the past, this is just an introduction. I would like just to give you, to classify 3 different contexts. These are examples of what I would say living agents. When you have the example of birds and they flock, you have school of fish, herds here, of sheep, bacteria. This is an example for living agents, in contrast to thinking agents, where you get crowds, human crowds, or traffic crowds. And then you can think of non-living agents like robots. That's called the rendezvous problem. We'll see that later on too. Peridynamics, pneumatic fluids. What is common in all these cases, without getting into the details, is that the interaction is local between agents and the neighbors in the spirit of what I showed before, and we are interested in the macroscopic description to see the large-scale patterns that are formed. In this case, it's just a flock, or in the case of opinions, we get a consensus. So the word changes from area to area, but the idea is to get this kind of global pattern. How does it emerge? How these patterns emerge from the local interaction? That's the basic framework. Now, in order to do this, there is no point in just jumping into the analysis, but there is a point to get, for those who are not familiar, at least to the leading examples of models along these lines. So let me start with the first. And the first is the Krause model. It's a model that was introduced by Krause and Hexelman in 1997 and on. And the state space, the properties, are just opinions, which I will denote by X. And we can think of the opinion just a scalar opinion. Let's say I have an opinion which I can quantify as a digit from 0 to 10. Or we can think about vector of opinions. That's fine. The question is, what is the dynamics? The dynamics would be exactly what we said before. This is the Krause model. I'm changing my opinion in the next time step by taking an average of all the opinions of my neighbors, and this is the average, and I are really the neighbors that participate in influencing my opinion. It is as simple as that. And this is, of course, an environmental averaging, and the Aij in this case are given by an influence function, which is simply the characteristic function of the interval 0 to R. So all those neighbors of mine whose opinion is not more than R away from my opinion will participate in influencing my opinion. And the degree turns out to be exactly an I. That's what we divide up there. And notice that this is a local model. Now, before I continue, So this is the beginning. We look at that and we say this is really a simple problem. What could be complicated in that? And just in order to intrigue you, I would like to mention that this model is extremely complicated, and I hope that by the end of the hour I will convince you how complicated this model is to analyze. Of course, there are many model questions which I know that will come up later on. For example, what is the meaning of distance between opinions? If we have a scalar opinion, clearly the difference between our opinions is obvious, but if we have a vector of opinions, it's not at all clear that we should use one of the standard metrics to measure the difference of vectors of opinions. But I will leave the issue of modeling aside, and I will continue with my mathematical approach. And now I write this Krause model as a model for alignment. So here's the difference between my opinion and the opinion of my neighbors. This is the frequency, this is the rate of change. And from now on, I will replace the fully discrete model by the semi-discrete, which is here, because I would like to concentrate on the spatial behavior. And here at the Aij, there is an inference function, and in general, it could be any inference function, it's part of the modeling. Notice that in the Krause model, if you remember, the inference function was some local function, it was locally supported, and hence we get local models. These are complicated to analyze, because they have finite support, and they are more realistic. And this is in contrast to global models, where phi has global support, that is, I will be influenced by the opinion of all the people in this room. And I will try to convince you that we know a lot about global models and we know very little about local models. So this we understand well, but they are less realistic. This we understand there are many interesting open questions which I will mention, but they are more difficult. There are many other more models in different contexts for this kind of opinion dynamics by a long list of authors. They involve social networks, evolution of languages, production networks, marketing, economics, pedestrian, traffic, Tour de France, gossiping, which is a very important human activity. In all these cases, basically, there are agents which are influenced their neighbors, and we try to understand, for example, when the gossiping process becomes a truth. Okay, so this is the first model of Krause and Hexelman, and we move now to the second model, which is slightly an outlier in the series here, but it is very important to bring it to you because it is a very important model which has a lot of impact, in particular in the physics community. And this is, before we do that, I just want to, otherwise it's becoming too abstract. I want to show you. Yeah, I didn't have time to do this, sorry. So that I trust myself. And now it works. So here's an example of randomly distributed two-dimensional opinions that they run in time. If you wait, you will see that these two guys, finally they get into consensus. You have to wait a little bit. That's it. And now we have 17 parties, and this will be the end because the inference function has a support which is less than the minimal distance between these two parties. They do not communicate. This will be the steady state. And this is just one example of what I'm talking about, realization of what we are talking about. Okay, so here 100 opinions lead to the formation of 17 parties. There is a question, what does it mean to measure the difference of opinions? We'll stop by that, and we'll go to the second model, which is the Vicsek model. The Vicsek model is slightly different. It was introduced in 1995 by this set of authors, and now we are talking not about opinions, but we are talking about birds. Every bird is characterized just by its direction, not its velocity, just its direction. The hidden assumption here is that all the birds travel with a fixed speed, s, and they can align their direction. That is, when we look at bird's eye, they change their direction, denoted here by omega, by taking a weighted average of the directions of its neighbors. Once we take a weighted average of the directions, we pre-multiply by the speed in order to get the velocity. But of course, doing that, it's not clear that we get direction. So there are two things which are important here. First, we add noise. That's different than what we had before, in addition to the alignment process. And once we add the noise, finally we normalize in order to get something on the unit disk. So this is the Vicsek model. And the other important aspect here is what are the weights? The weights are the inference between where bird I is and the other neighbors are. Notice that now I'm talking about physical location, not just the opinion, and what is the location. So there is a velocity, there is a location, and what is the location? The location integrates the velocity. So actually there is a dynamics here basically for the orientation, or if you want for the velocities, and the location is integration of the velocities. So this, in contrast to what we had before, this is a second order model, because we discussed the velocities and we discussed the physical location. Before there was only one scale, which was the opinion. Fine. So this is a second order model. We can write it as an alignment dynamics. Here it is. It's a semi-discrete version. It's slightly more complicated. And as we can see, there is something beyond just environmental averaging. I will just put it on the slide, but I will not elaborate anymore. I should mention that behind every such model, there are really hundreds of papers. I do mention the Vicsek model in order to show you the following thing, how the Vicsek model looks in time. So this is on the two-dimensional torus. And what you see here is the dynamics of the birds, which are driven by the Vicsek model. What is important in this case, I know that you will try, I will talk while you try to identify here some periodicity, you will not find it. There is no periodicity here. The two important parameters that play a role here are the intensity of the noise versus the intensity of the interaction. And these two parameters are important because the relative size dictates whether the Vicsek model has a phase transition, which ignited a lot of literature, particularly in the physics community and in the mathematics community. And the phase transition is important because then local signals can propagate very fast. And I just mentioned here there's a lot of important work, so that you will see of Vicsek, of these authors, and there's a lot of discussion why the phase transition, which is already observed in mesoscopic scale, not just in the large scale, is important in reality. You act local and you think global. And here just a collection of the authors, Ian Cousin, Bialik, Wilson, and so forth, with hands and many different contexts. So I'm doing a little bit of justice to this topic, but I think it is important to bring to those who are not familiar the Vicsek model. Moving from the Vicsek model to the next model, it's slightly simpler. This is another very influential work that was introduced in 2007 by Cucker-Smale. It still has to do with birds. Now every bird has a full velocity, not just orientation, and they change, the rate of change of the velocity is a weighted average, is an alignment process with the velocities of the neighbor. So in some sense it's simpler. We put the noise outside for the time being. And what are the weights? Well, the weights really have to do with the influence function depending on the difference of location of bird I and bird J. Just as before, we have now a second order model, which is given here. It's quite simple. And in the original paper of Cucker-Smale from 2007, it's very important what kind of function phi we take into account. In the original paper, they took an influence function which is decreasing. Makes sense that as our neighbors get away from us, their influence on our changing, our influence on our behavior, on our velocity is decreasing. They assume that they decrease polynomially with some power. It turns out that this power has some critical value regarding the large time behavior of Cucker-Smale, and it took some time to analyze this. So this is an example for a global model. Because in this model, of course, every bird is influenced by every other bird. The support is global. This is in contrast to local model. In local models, remember when the degree was just the number of local neighbors, if you take this function phi to be locally supported, then every bird will just feel its immediate neighbors, and then their neighbors will feel their immediate neighbors. These are local models, and they behave completely different, as we should see. So again, the global and local, I'm trying to emphasize the difference between the two, and there are a lot of works. I mentioned just here a few of the important works that were done in the last decade or so in this topic. So this is the third example. I entered into this subject exactly with the model of Cucker-Smale, criticizing that the Cucker-Smale model is, in a very fundamental way, is limited. And it has a serious shortcomings, which I would like to share with you now. So here's the issue. the limitation of the Cucker-Smale model, the state space is not homogeneous. So let's assume, here it is, that there is a small group of birds flying here. I call it group G1. I will assume that I'm here. And our intuition is the following. If there is another group of birds, which is really far away from group G2, from group G1, we assume that the influence of group G2 and group G1 should be minimal, be negligible, simply because they are far away. And that's what we feel. But this is not the case. Let's see why this is not the case. So remember, what I wrote on top here is the Cucker-Smale model. Here are the influence phi ij stands for phi of xi minus xj. We normalize with the total number of birds. This is the original Cucker-Smale model. And here are the alignment terms, and everything seems to be rather simple and straightforward. Well, let's see. If you have group G1 and group G2, so and this is me, then I break the influence of my neighbors in group G1 and my neighbors in group G2. And I agree, since the influence function is decreasing, and since the distance between me and xi, at point xi, and these are at xj, which are very far from me, of course this phi ij there will be really small. So the influence of group G2 will be minimal on me, that is my members or my neighbors in group G1. That's correct. However, we agree that we have to, according to the Cucker-Smale model, we have to normalize by the total number of birds, which is denoted here by n. Now, here we have n1 and n2, which is much larger than n1. So if n2 is much, much larger than n1, basically I will have to stop. This looks a little bit strange because we just did a regular averaging over all the birds. So what can go wrong here? What is wrong if we just averaging? That's what we do in statistical mechanics. So the thing that is wrong here is that this is a scenario which is far from equilibrium. And we have to take it into account. We are not close to equilibrium. And one way to solve this is the following. So this is a model that we introduced in 2011 with Sebastian Moch. Instead of dividing by the total number of birds, and now you see the importance, we divide by the degree. And what is the degree? The degree is the sum of phi k, the total influence of all the birds close and far together. So it seems like a small change, but it's not a small change because let's see what happens with this model with my group G1 and G2. So what is the degree? Before we divided here by n, but what is now the degree? So I'm here, let's compute the degree. We have to compute all these phi ik. So this will contribute this and this, but all these guys, all these birds which are far away will contribute a negligible amount to the total degree. So in fact, in this case, the degree will be 4, essentially 4. So you get a model which adapts itself in the normalization to the immediate neighborhood for close to equilibrium and to far from equilibrium. And now you see how important it is to divide by the degree rather than the total number of the members that participate in this dynamics. But the price that we have to pay, before when we divided by n, we had a symmetric matrix, and now we have a matrix which is not necessarily symmetric, which complicates the analysis of the large time behavior of such models. Okay. If the problem was symmetric, then basically we can write all these models in the following form. We have the phi ij, we have the degree here, so this is the matrix aij, which could be symmetric or non-symmetric. And in fact, we can write it just as the matrix A minus V. So if I will denote the Laplacian as I minus A, the Laplacian associated with A, this dynamic is simply dictated, the right-hand side is dictated by minus the Laplacian associated with A. When the matrix A is symmetric, then it's easier to analyze. When it's not symmetric, it's considerably more complicated. Okay. So close to equilibrium and far from equilibrium, and this concludes my 4 examples with which I would like to work now in the general formula. Before doing that, I would like to mention that there are many more models, and I cannot compress it into 1 hour, and they come in different contexts. And let me just try to make a short summary of these different models from different disciplines. So in biology, there are many types of this kind of collective dynamics. Typically, they involve flocks and swarms and colonies, and the typical question is how they are being formed. There is no Newtonian mechanics, so the question is, what are the rules of engagement? What are the phis? And agents are different, so these are patterns system specific. So the question is basically to distinguish, to catalog the different cases, to make a different list of what is going on. It's separating between the different cases. This model also comes in physics, as I mentioned. Over there, the culture is completely different. It's just the other way around. Indeed, the models are different, but there is deep analogies in patterns of equilibrium. So concentrating on models which are close to situations which are close to equilibrium, they seek stability near thermal equilibrium in terms of statistical mechanics. So even though an agent acts differently or similarly, still they want to unify and to classify the different models under fewer collective sort of list of collective motions. So just the other way around. But it's not just in biology and physics. In computer science, also this question comes up. Over there, the questions are about agents which form networks, as we shall see soon. Very important is the interaction between the agents, and once we want to understand the question of clustering, we have to get into spectral theory of graphs, which I will not do, but they see it from a completely different perspective. It's not the dynamics near statistical mechanics, it's not to catalog different cases, it's the dynamics over networks. And this question also comes in engineering. Over there, the questions are completely different. They want to control the dynamics by adding external forcing. They want to optimize the traffic, to improve the safety. The same kind of models. And it's quite impressive to see how this type of models spread throughout different disciplines with different kind of questions and different kind of languages. And then, in math, we have the experiments, we have agent-based modeling, kinetic models, and macroscopic models. This is what I would like to talk today. And we would like to understand how we get from the modeling to numerical simulations and to analyze, we'll present these two questions of large time behavior and large crowd behavior. There are also different tools here, which are highlighted here in blue. So what are the two questions? Again, I would like to know what happens as t tends to infinity. And I already mentioned that I would like to distinguish, I have to distinguish between global and local models. And I already mentioned that before we got 17 parties, we may get one party, which I will call consensus. When do we get 17? When do we get one? Why? I do not know the answer to that. I will share with you what we know and what we do not know. And then the second question is, what happens when the collection of agents is very large? We are really not interested in all the details. We would like to see the macroscopic behavior, so this will be the second part. That I will talk about social hydrodynamics and critical threshold in social hydrodynamics, a topic which might be more related to some of you working in hydrodynamic descriptions in different contexts. Okay, so this is the rest of the talk, large time behavior and large crowd behavior. Let's start with the large time behavior. So formation of k parties. So here's an example. This is time. We take the distribution of opinions, which are scalar opinion running from 0 to 10. We take this Krause model that I mentioned at the beginning with some function phi, which is locally supported. And you can see that in one case, as time goes on, you get 5 parties. And this is it, because the support of phi is less than the distance, the minimal distance between these parties, so they cannot communicate anymore. That will be the end. And in another case, what you see here is that we get consensus. They all converge to the same thing. When do we get this and when do we get that? It's an important question. This is a generic question. It has nothing to do with the specifics of the model, but we would like to know what's really important in this case. So here's the question of consensus that I have. This is the case k equal to 1, where all the opinions converge to the same limiting opinion, that is the consensus. Or we can talk about the case of a flocking. What is a flock? Where all the velocities approach the same limiting velocity while the actual distance stays bounded. So we can talk about the flock. This is the diameter of the flock. And in this flock, they all approach, tend to the same direction. When do we get one flock? When do we get consensus? I should mention that these questions fall under the category of clustering, and there is more than clustering than what I can show here. For instance, it's important to mention the mean shift algorithm, which is in spirit exactly what I'm talking about here. Again, I do not have enough time, but the mean shift algorithm, which is a non-parametric example for clustering, a non-parametric algorithm to identify clustering, evolved according to dynamics where there is an alignment from the mean, and this is the definition of the mean, and there is some inference function, and you can see some sort of similarity. Okay. So what about the large time behavior? Let me slow down here. This is what we are talking about. We have a vector of properties, and I try to convince you that it covers different cases, orientations, velocities, opinion, and we change our opinions by taking the weighted average of this gradient or alignment, whatever you want to call it. So let's rearrange the term here. Like so, I took alpha equal to 1. I rearrange the term, and I get the following nonlinear alignment, that the new property is 1 minus delta t, the old property, when you rearrange the terms, plus delta t times the matrix A, this is the action here, times my vector P, but the action, the matrix A given in red, depends, this is the nonlinearity of the current scenario. So what can we say about the time behavior, the large time behavior of this model? Well, let's assume that we can find a contractive metric such that after acting with the matrix A, we get a contraction relative to the metric of the vector P. So let's assume that the before and after is contractive if we can find the right metric on this vector A, on this on the space of vectors for the matrix A. I don't know what this metric is, but let's assume that we can get a contraction where eta here given in red is a number which is greater than 0. So it means that there is some sort of contractivity. The only question mark is, what is this metric that I should measure the contractivity with? But let's assume that we have such a metric. Then it's very easy to see, if we take this metric, we apply it here, then the metric at the next time level is less than 1 minus delta t times the metric at the previous time level, and then we have delta t, and now we have contractivity with 1 minus eta. You rearrange the term, and you conclude that after one time step, there is a contractivity by the amount 1 minus eta delta t. So this is one. For one time step, it means that if we will reiterate, then the contractivity will imply that this metric of the vector of properties will go to 0, and hence the property will approach a limiting case if we find the right metric. What metric it is? In fact, it's not a metric, it's not a norm, it's a semi-norm. And let me give you now 2 examples for this kind of metrics. Okay, so we are looking for contractivity and we are looking for the metric. So here's the general recipe. I suggest that we will measure the metric for the collection, for the ensemble of agents by taking the simple diameter, the maximal distance, the maximal difference between the property Pi and Pj when we maximize this distance over all the members in our community. Okay, so this is the diameter of the group. And this metric we ask, is it true that there is a contractivity in the manner that I mentioned before? If there is, it means that the diameter is shrinking in every step, and in the long term, the diameter will go to 0, which means that they all go to the same direction. But is there such a contractivity? The answer is yes, depending on the property of A, and the shrinkage parameter eta here is given by the coefficient of ergodicity. The coefficient of ergodicity is given by this formula, which you should not remember. However, I would like to tell you that first of all, this coefficient of ergodicity and this statement is sort of rediscovered every 20 or 30 years from Markov on, myself included. So this is the final answer here. This is the coefficient of ergodicity, and I gave you a reference. But what I would like to notice is the following. The coefficient of ergodicity, which would like to be positive, in this case it is positive if all the elements of our action matrix are non-zero. What does it mean? Remember that the Aij are given by the inference function normalized appropriately. And in particular, if the inference function, as you can see here, never vanishes on xi minus xj, then the eta will be bounded away from 0, we will get contractility, we will get consensus. What does it mean? It means that eta, this coefficient of ergodicity, assuming that the inference function is decreasing, is always greater or equal than the phi over the diameter of x minus t. Namely, let us assume, and this is part of the model, that the inference function is arranged in such a manner that everyone talks to everybody else. So phi of the diameter never vanishes, because eta is greater than this lower bound. So let's assume that every agent interacts with every other agent. No one is left outside. Then the conclusion is that the diameter decreases by phi with this lower bound, and therefore we will get, in this case, consensus. So what we see here is that as long as there is a communication between all the members of the community, then eventually they must converge and they must get into consensus. The same thing happens not just with opinion, the same thing happens with unconditional flowing. In this case, the properties are the velocities, if you remember, and it turns out that if the diameter of the velocity is less than the integral of the inference function, it follows it's slightly more complicated. There is a contractility of the velocities in terms of the diameter of the location, and then one can find a decreasing energy functional. This is the reference of high and jump on u, and using that, the conclusion is that if the inference function not only has a global support, but if the integral of the inference function diverges, then there is unconditional flocking. Case in point, if you take the example of Cucker-Smale, which I mentioned before, with this kind of decreasing inference function, it turns out that with this kind of inference function, there is an unconditional flocking, independent of the initial configuration, if and only if beta is less than 1/2. Because then and only then, the integral is infinite, and it essentially means that we need an interaction between the birds, all the birds, with sufficient strengths for those birds which are far away. Okay, question number 1. In this case, we get a limiting velocity. What is this limiting velocity? It's not clear. Okay, so this is the example of general models. Let me now be more specific about symmetric models. Here they are. In the symmetric models, I would suggest to use a different type of contractility. I suggest to do it simply because I'm trying to share with you a sort of a fly over the literature. And in the symmetric case, the other kind of metric that I will use is this L2 diameter, namely the sum over all ij of pi minus pj squared. So this is a natural candidate for the diameter of a group when you get to the symmetric case. And indeed, what we would like to know is whether or not there is this kind of contractility. And if we have this kind of contractility, I want to remind you, then we get a flock, consensus, and so on. And this will be in the symmetric case. And in the symmetric case, there is this type of contractility. And now the role of eta is played by the second eigenvalue of the Laplacian associated with A. What is the second eigenvalue with the Laplacian associated with A? It has nothing to do with anything. Well, this is called the Fiedler number. And when it characterizes the Fiedler number for the symmetric matrix A is the graph connectivity. So let's elaborate a little bit about that. If we have a matrix A, if all the elements are positive, in this case, and everybody communicates with everybody else, then we know that we get consensus. But what happens if some of the members in this community do not communicate with other members? Well, then we run into the issue of graph connectivity. It is defined in a very complicated way here. Let me tell you what it means in practice. It means that I may not be in contact with all the members in this room. However, I will be in contact with you. You will have in contact with other members. And in short, there is always a path from every one member to any other member in this room or in this group. So if the graph is connected in the sense that there is a connecting path between every two agents, then, and only then, lambda 2, the Fiedler number, that's what it characterized in the symmetric case, is bounded away from 0. If it's bounded away from 0, then this contractility factor really contracts, and then we get a flow. So in fact, what we need is connectivity. We don't have to talk with everybody, but we just would like to know that we are connected. Well, here's an example where we get 5 clusters. So what happens here? It's interesting. We started with all these opinions which are clearly connected because and you see that every other opinion is really next to the previous opinion. And as time goes on, we got here, remember, 5 parties. So what really this example shows that we started as a connected group and connectivity is lost. On the other hand, we started as a connected group and connectivity remains, and hence you get flocking. In this case, it actually was a consensus. So connectivity can be lost or can actually propagate. So question number 2, determine K, the number of limiting parties, and in particular the question is, when is it the case that we get a consensus, namely K equal to 1, depending on the local case? And finally we come to a very deep question, because we do not have Newtonian laws, and we usually have, in realistic case, influence functions which are problem dependent. And we see that when we have local influence functions, the large time behavior is not at all clear. And the difference between having a consensus and having 5 parties is really very important. So which is which? What is the answer to this case? In order to make this question even more urgent, namely the propagation of connectivity, let me discuss about how the rules of engagement influence the overall behavior over time. So if you remember, before I took in the Kuramoto model, the influence function, which was the characteristic of an interval, in this case I take the interval 0, 1, just to simplify matters. So this is an example for an influence function which is decreasing, which makes a lot of sense. And you see that we start with a collection of opinions, and they form, in this case, four parties. So what does it tell me, in this case of model? It tells me the following, that in this model, everyone who is 1 away from my opinion is taken into account, and everybody that is further away, I completely ignore. According to this rule, when we run this dynamics, we get 4 parties. Here is a different model with the same distribution here. We take we take an influence function here 1. However, those that are really close to me, this is between 0 and 1 over square root 2, I take less emphasize. So instead of having a decreasing influence function, I increase the influence function before stopping it to be with finite support. I ignore those that think like me. The net effect, I get a consensus. So is this unique? Is this special? Well, it turns out that this we call homophilic dynamics, and this is called heterophilic dynamics. So homophilic, we align with those that think like us. It's intuitive. Heterophilic dynamics, we bond with the different, which is counterintuitive. So now the question is, homophilic versus heterophilic, what happens in these 2 cases? Well, we see, we took here the values A and B. So you remember, A is those that are close to me, B is the intensity for those that are further away, and you can see that as I increase B, as I become more and more heterophilous, the number of parties decreases all the way to 1. The more heterophilous you are, the more you pay attention for those who are different from you, the more you increase the likelihood that you will get a smaller number of parties, and eventually you will get into consensus. And this is not a coincidence. In almost all cases, there is a logarithmic decay for the number of parties, the more you become heterophilous. It's not a deterministic statement, it's a probabilistic statement. The problem is actually to understand why. Namely, the problem is explain why as the influence function phi increases and becomes more heterophilous, there is more likelihood that the Fiedler number will remain positive and the graph will remain connected, and as a result of that, you will get consensus. Okay, the reason that this is a probabilistic answer and not a deterministic answer is because there is an instability for local interaction under a fixed number of agents, so one has to make some probabilistic statement here, and there is an ongoing work in that direction. These questions were raised in this recent Siam review in 2014. And this will also conclude my discussion about the large time behavior, but before I do that, I would like just to mention, to conclude with the following comment, there is much more than just environmental averaging. I don't want to give you the wrong impression that everything is environmental averaging. It's not true that everything, as we know from reality, evolved into finely many clusters. And here's an example. This is the general paradigm that was introduced by Craig Reynolds. We discussed here just an alignment. So here's an agent, and these are the agents around it, and they try to align with this agent. However, this agent also has a repulsion with those agents which are very close to it, exactly as described here. So there is an attraction, there is alignment, and then here there is a cohesion when they try to stay together. So there is a three-zone region. And this kind of model was introduced in 1997 by Craig Reynolds in this paper, which was very influential. And this point that I always mention, that even if you work, you notice that most of the works they introduced in this literature in the last 20 years, and even if it doesn't bring you the Fields Medal, it may bring you the Oscar, because he received the Oscar for this paper, because this was the first realistic modeling of birds, using this kind of paradigm of repulsion, attraction, and alignment. But there is more than just beyond the environmental averaging. There are external forcing, which lead to pattern formation. And of course, we also, it's just too general. We have to differentiate between, if you remember, living agents and then non-living agents, and social atoms are not the same as atoms. And just to give you an example, we conclude by this part, by example of thinking agents. So here, just think of this question that I'm raising here. There is a distinction between different types of agents. So here's an example of what we think about birds or robots, that they act along the radius vector connecting two agents. Is this the case, really, that we always act along the radius vector? Here's an example which I'm offering where I will act not if there is an agent here, not where, if there is an agent here, not where it is, but I will act or will be influenced by the projection to where he was, or it was, closest to me. So we take into account the projection rather than where it is. Case in point, think about ants and think about smell rather than vision. Or think about the way that you are influenced by opinions. You're not always influenced by a person with his current opinions. You take into account what were his opinion or her opinions at the point that was closest to yours. This is very relevant, completely changes everything. In what way? Well, it's very simple. If you ignore the red term here, that's what we had before. If you add the red term here, this is just making the projection of this agent along the straight path from some agreed origin, and then I take the projection of agent J and I measure the difference between my state and the projection of agent J, and I would like to see what happens there. That's it, that's the only difference. And all the terms here in the neighborhood basically means that I take those that are ahead of me, because there is no point to take the projection for those which are behind me. What will be the next effect? Well, okay, so there's a lot of stuff here that I will skip. Taking those, the tendency to move ahead. This is basically taking into account the tendency to move ahead. And you can see the example here. Yeah. We started with three collections of random set of opinion. And what you see is that there is no concentration to one or more parties, but there is a concentration along lines, which makes perfect sense. And in each line, the guy that's staying here is, of course, we will call it a leader. And these are following the leader. And when you come to think about it, that's exactly what we should get. So this is a different kind of collective behavior with large time behavior, with large time, collective dynamics with large time behavior. And you now realize that actually we can go well beyond environmental averaging, and all the questions that we had before apply here, and so on and so forth. And I have to stop at some point, so I think it's a good point to stop this part which talks about the large time behavior in collective dynamics. And I would like to conclude with the last part, which is now large crowds. And this is usually the point where I lose, if I did not lose everybody, I'm losing half the crowd. I'm just telling you from experience, because I'm going to talk about kinetic description in my passage to the behavior of large crowds. So just bear with me 2 minutes. So we would like to have a description for large crowds, and what we are trying to do is this. So this is the agent-based models. This is a very nice example that Sebastian Moch made. So this is the agent-based model. That's what we discussed so far. From the agent-based model, we would like to move into a kinetic model, so we get this kind of transport equation. And we are not interested really in the details. We just understand. We'd like to understand where the wind is blowing. And finally, from the kinetic model, we will get the macroscopic description, which is maybe more familiar to most of you. That's what we would like to do here, and the way we do it is now. We start by taking what is called the empirical distribution. So we put a Dirac mass at every point in x and every velocity vj. We take the average, this is called the empirical distribution, and we just assume that as n tends to infinity, there is a limiting function f depending on time, space, and velocity. It measures the probability of particles to be at time t, location x with velocity v. This distribution function just satisfies the Liouville equation, which is given here. And the most important in this Liouville equation, there is a transport equation with velocity v, and here is the interaction between the particles. This is where the models enter, and here's the interaction term. It's a bilinear term, and here's the one distribution in x and v, another distribution in y and w, and now these two agents, its probabilities, they interact according to a kernel A of x and y. And what is this A of x and y? Well, here's our influence function that we mentioned before, and it has to be normalized with the degree, and the degree is either 1 in the case of the Cucker-Smale model, or in the model that we introduced later on, the degree is given by this normalization factor. So we will not get into the details, except for remembering that actually the agent-based model here survives. It survives by this kind of bilinear interaction. And what is the large time behavior? In this case, there is noise in the diffusion, and there are many other aspects. Here's the large time behavior for that, for this kinetic description that I just wrote to you. So as t tends to infinity, what you get is a collection of Dirac masses around some macroscopic velocities and macroscopic functions, which we call the densities. In particular, in the case of locking, if there is one flock, what you get is the density, and you get one Dirac mass, which is given here. So this is the standard form that you should get in the large time behavior, and it looks like this. So basically, when you run this kinetic description, what you will get is that there is a finite diameter here. This is the distribution in density space, and the velocities will approach some limiting velocity, which are called u. And what we are interested in this kinetic description, my 2 minutes for kinetic description are about to be over. I'm interested in this u, depending on t and x, and in this rho, because these are the two parameters which describe really the kinetic behavior. How can I recover rho and u from this kinetic description, kinetic distribution? Well, once I have this form, I can recover rho, which we call the density, by taking the integral of this Dirac mass. And if I multiply this Dirac mass by v, you can see that I can recover not rho, but rho times u. So it leads us to the conclusion that by taking moments of the kinetic distribution, we can recover the macroscopic quantities. Of course, if we take these moments, then we will run very quickly to the question of dealing with higher and higher moments, and this requires some closure on this stress tensor that I will avoid. Okay, let me show you what we get when we do this kind of moments, taking the moments. We will first of all ignore all these stress tensors in order to simplify matters, and we end up with a macroscopic equation for the density and the velocity, and these are the familiar equations. Namely, we have the mass equation that we are familiar from the compressible Euler equations, and then we have the momentum equation. So here's the momentum for the velocity, but with one important difference. And the difference is that on the right-hand side, we now start to see the model that we deal with. This is the velocity, and this is the average velocity. Remember, I started this talk discussing about the process of alignment. And here you see the alignment. At every moment and at every place, the velocity tries to align itself with this average. And what is this average? Here it is. The average is given by the average of the momentum, normalized by the average of the density. And what is this average bar? The average bar is given by convolution with the influence function phi, which comes from the agent-based analysis. So there is a hierarchy of arguments here, but at the end what we get is this kind of difference between U and its average. And the difference between a value and its average is a Laplacian. So this is a continued version of the Laplacian that we had before in the agent-based dynamics. And now, of course, we have different models depending if it's Cucker-Smale and the normalization and the degree, and I have to skip it. And of course, if we would like to take the case of tendency into account or the projection, you can see here also the projection that I mentioned before, and you understand that we can now inject into this kind of models everything that we had before. It looks very familiar. The only difference is what we have on the right-hand side. What we have on the right-hand side are this kind of local Laplacian. Indeed, if we take phi and we really shrink and dilate the Laplacian in the appropriate scaling, we really get the usual Navier-Stokes. I'm not interested in Navier-Stokes and not in fractional Laplacian. I'm interested in local phi's. So I call this dynamics of non-local means. And here's an example, again, thanks to Sebastian Roche, for those who suffer the kinetic description. So what you see on the left is the particle description. These are all the details that you want, but it's too much. And here's the macroscopic description, and that's what you want to see on a macroscopic level. And you can see that what you see on the left is really observed on the right, but on a macroscopic scale. So either you want to see all the details, or you just want to see the concentration. Okay, so we would like to study the macroscopic behavior. I'm going without time, sorry, so we have only a few minutes. So this is the macroscopic equation, and then we assume that the phi will be a global inference function, and here's a theorem which Chan with 10, and the question is what is the large time behavior for this system, and the statement is the following here. If there is a smooth solution for this system of equation, then the global smooth solution is that everything flocked together. Everything we have done in the agent-based dynamics transport to this framework under the assumption that there is a smooth solution for this system of equations. And as we know, the question of existence of smooth solution for Euler-like equations is a fundamental question in the usual Euler-Navier-Stokes equation. So it brings us to the question, the proof is Lagrangian. Is it true that this equation admits global smooth solution? This will be my last question that I would like to address. So let's take the one-dimensional case. It's a one-dimensional alignment. Here's how it looks. A mass equation. Here's Berger's equation. But you do not have viscosity here. What you have is a localized viscosity. Because this is the difference between U and the average of U. So who wins? Do we get finite time breakdown or do we get global smooth solution? The answer is neither. What we get here, if you allow prime to denote the partial derivative along the particle path, you get here the Riccati's equation. I just discussed this today with so. But on the right-hand side, you get a term which has to do with the interaction due to the inference function. When you rearrange everything correctly, it turns out that the term on the right-hand side, this non-local mean, is responsible for shifting the Riccati's equation, and you get this kind of Riccati balance by alignment. So this is the Riccati, this is the Riccati, this is the alignment, and the conclusion is that there is a global smooth solution if, and only if, the initial slope is allowed to be negative, but not too negative relative to the initial density. So there is a critical threshold, there is a conditional regularity, which is not characteristic in the general case. In fact, this is not only in the 1D, but it's also in the two-dimensional case. In the two-dimensional case, we have to study this equation in the same manner, and we get that there is a critical threshold, there is a global smooth solution, if and only if the initial divergence, instead of the initial derivative, is above certain function, which I will not write here, depending on the density and on the spectral gap. Spectral gap is the difference between the two eigenvalues, the eigenvalues of the stress tensor, which is given here. This is a 2x2 stress tensor. And how do we get the spectral gap? We get the spectral gap if we write now the Cucker-Smale hydrodynamics, which is written here. We write the equation for D. We get the same Riccati equation as before. Notice the D squared. We get a lot of stuff on the right-hand side. We have to do precise computation, and we get, if you take the trace of this matrix, you get exactly the divergence. The divergence is being transported. You get a lot of terms on the right-hand side. They're worked out correctly. You can add them up. There's one thing you cannot do. Look at the trace of this squared. And the trace of this squared, D is this stress tensor, when you come to think about it, is exactly, so this is the sum of the square of the eigenvalue. And lambda 1 squared plus lambda 2 squared is exactly the square of the sum plus the square of the difference. And here, the spectral gap enters. So there's a further work, and this is a short description, which has to do with the initial spectral gap. And under this condition, you get a critical threshold behavior for the two-dimensional floating hydrodynamics. Let me stop here. Let me thank you. Let me just mention that this work is part of this Kinetic network that was mentioned in the introduction by Alina, which has to do with the kinetic description for many different problems in chemistry, social sciences, and different models in biological processes. It's spread between the three main hubs. The main one is in Maryland, UT Austin, and Madison, and there are many nodes, and I'm happy to say that also North Carolina State University is one of nodes, and let me thank you at this point. And one last thing, one of the advantages of talking about this topic, that everybody sends me nice videos about that's it. So that's the real end. Thank you.
This question could be completely ridiculous. I'm wondering whether, the first half of your talk, can this is being thought of as some kind of gradient dynamics?
Well, it depends now. Yes, okay, so now, okay, so this is, I should have mentioned that, but it depends whether it's first order or second order model. In the first order model, it could be considered as a gradient dynamics. In the second order, it's slightly more complicated. It's not direct. The first order model can be considered as gradient dynamics. Yes, yes, absolutely. I did not write it in this form because I want to emphasize the role of the inference function phi. If you look at the literature, so I used a little bit here the literature because I compressed a lot. What you will find, you will not find phi, but you will find the primitive of phi. Everything in the primitive phi is sort of the potential. Once you take the gradient of potential, that's what you realize. Yes, that's exactly what you realize. You're absolutely correct.
Eitan, when you transitioned from your first part to the second half, when from small numbers of agents to large, when you started your kinetic description, maybe I missed something, but it looked like you immediately built all the description using just what in statistical mechanics would be a single particle distribution function. Yes. Maybe I'm wrong on this. Maybe
no, you're right.
So why why was it immediately reduced to single particle as opposed to BGK chains or something like that? I mean,
yes. Okay. So there is a of course the path. I'm hiding a lot of unpleasant aspects here. So just by the statement that Fn converges to some distribution limit. I think in this case it is justified. It's not the case of Boltzmann where there is a singular interaction. The realistic scenario here is that you have phi which is local, there is no blow up, and these are really justified. And there's a lot of work that justify the passage as n tends to infinity to this kind of Lasso description. You can justify this. It's not like the Boltzmann case. Remember the big difference. The realistic difference is that when you have collision between particles, they have to collide. Here there is no collision. There is just influence. I don't need them to get close. Everything depends on the inference function. It's a completely different behavior.
And collisions are also, we call it collisions, but if it's, typically it's a cross-section. They do not necessarily physically collide. They just do the trajectories, right?
Correct, but then it's important that this potential is singular. If it's not singular, then it's a different story.
Okay.
It's a different story.
Okay.
More questions? Yeah.
So in the part where you show a model, there's a leadership emergence.
Yes.
So I assume in your model, every part intrinsically they have the same behavior, it's just their positions incorrect.
So in this model, the key question is what is the origin? Because the hidden assumption was that I look at my neighbors and I assume straight path, and I take the projection into a vector, right? Radius vector from the origin going forward. What does it mean to go forward? And you immediately run into a question which is very relevant. What does it mean to go forward? It means that it has a meaning only if you and I agree what is the origin. Otherwise, there is no meaning to what it means to go forward. It's because we are trying to go away from the origin. So you run into the issue of modeling. I brought it up as an example for something beyond environmental energy.
So if not, I would like to thank you